Alright guys, welcome back to these physics tutorials. We are still in the process of making up stuff. So now, let's look at another very interesting physics practical experiment. We want to look at this analog potentiometer and we see what is the relationship between the resistance and the length. You know, from Ohm's law, you already established before that if I have a potential across and there's current flowing and there's a resistance, then there is a business between the current and the resistance. From Ohm's law, we know that I is V all over R, and it means that if I'm increasing the resistance, then the current is supposed to fall. They are inversely proportional. So, and we also established inter alia that the resistance factors that affect the resistance of a conductor includes the length of the conductor. And we want to relate that length of the conductor by its resistance. We know that the longer the conductor, the more the resistance offered to the flow of a current by that conductor. So that the relation between the length of the conductor and the resistance is directly proportional. So if we know the relation between current and resistance, and we also know the relation between the resistance and the length, then we can combine the two. We want now to look at how the length of the conductor, in this case, is going to be the constant time wire, how it is changing with respect to the current. And as the length changes, what happens to the current? We want to investigate that. So as a science investigator, we still want to investigate these properties. We want to see what will happen between what will happen with the current if I'm increasing the length, and by extension, if I increase the length, it means I'm increasing the resistance, because resistance is directly proportional to the current. So note this. So I can as well look at it and see whether it's possible that I will have the length there, because I have said resistance is directly proportional to the length. So now there is a resistance wire on this our experiment. So I just want you to note what we are trying to investigate as a science investigator. We want to investigate the relationship between the current flowing through that conductor and the length of that conductor, and by extension the resistance, because the length of the conductor is directly proportional to the resistance. So in other words, we are trying to look at what happens to the current flow if the resistance increases, and vice versa. So that is what we want to investigate as a science investigator. So guys, let's keep going and we move. My name is Samuel D. Koidia, don't forget that. So now we move. This is the, I want to give you a couple of materials here, so you become accustomed to them, because we are going to move along with that. So this is AC is a potentiometer. That's what's here. You have the potentiometer here. This is the potentiometer. Now this potentiometer it's an analog potentiometer, don't mind me. Now we have this potentiometer has a meter rule. That's the meter rule somewhere there. That's why it's called a potentiometer. It's a meter. The meter is 100 centimeters. So it's potential. It measures potential difference much more. So we can compare potential difference between materials using the potentiometer. So now we look at the length over there. It's also called a potential divider. So you don't miss the two. It's also called a potential divider. So now we look at the length here. This is the meter rule. And on this meter rule, we have a constant time wire. We have a wire that's going to be the conductor. And this constant time wire, we are going to vary the length of the constant time wire and see what will happen with the current. And remember, we said that resistance is directly proportional to current. So if I change the length of the constant time wire and the length is changing, then something will be happening to the current. Because if I change the length, the resistance also changes. As the resistance changes, then we expect the current to also change, because current and resistance are inversely proportional. So watch this out. This is the constant time wire. So in some other analog potentiometer you see around the laboratory, you see the wire is right on top of this. But this one is just a multi-purpose. We have placed the wire here so that we can, it's just a scale. All these rules are all scales. This rule is only to help us maintain the position of where we are going to put we want to increase or decrease the length. Where to put is what this rule is going to help us to see. So now we have the scale there, which is the meter rule, and we have got the constant time wire, which is going to form the loop. So I've shown you that already. So now we look at the next materials here. These ones are called connecting leads. You know that already. It's connecting wires or leads. You have them there. And you have a crocodile clip. That's a crocodile clip. It's a crocodile clip there. So we have that. We have a crocodile clip attached to this connecting leads, and it can help us do a lot of connections there. So a crocodile clip attached to that. So that's what I've done so far there. A crocodile clip. Then we'll have a battery holder here. You can look at this. This is not too sophisticated. I have a sophisticated type, but this time I just decided to use something that is homemade, you know. So you look at this. This is a sophisticated battery holder. This is a battery holder. So you have the black here is the negative terminal, and this other one must be the positive terminal. So now this battery holder is holding only 1.5 volts here, but I wanted to use I wanted to do a 3 volt battery, so I decided to avoid this for now and now use the one I have made so far locally. So this is a battery holder. You have seen this in some of your labs. You have this already. So what I've done here is you can do this for yourself. It's simple. You just look at you can look for the touchlight, a touch battery, a touchlight stuff, and you look at the back of it, the terminal is at the back. I just remove that terminal and fix it right here. It serves as that terminal. So this is the crocodile clip. You know that already. These are cells in there. You already know the cell. This is the battery cell. This is the battery that is the cell. And this battery cell, I'm using the 3 volts here. I'm using 1.5 and 1.5. So I'm using a 3 volt here. But I just want these terminals to be fixed, so I brought in another one to make sure it holds the terminal very well. So it is not actually part of the circuit, it's just holding this terminal so that I clip it onto the positive terminal. So it means that from that row here, I met the positive terminal somewhere here. And that positive terminal is the long line here. So it is this line here is this one that's coming. It's coming from the 0 point of the potentiometer, that's 0 there, and it's coming to that point, that is to the positive terminal. The long line here is the positive terminal. Let me just write it for you. This is plus and this is negative. So now I have attached it to the positive terminal. That's the positive terminal of the battery. You already know the positive terminal of the battery. This is, let me show you. This is the positive terminal of the battery. This is negative terminal of the battery. This is positive. This is negative. So now I have connected it to the positive terminal somewhere there. So from that potentiometer point, it arrived at that positive terminal. So I'm just using this to make sure it is firm. It doesn't move. The terminals are fixed there. It's one precaution that you can take. So that is it there. So let me just fix this one there to make sure this positive terminal is fixed properly. So now I get it there. This is the, so if I enter positive, I should take off negative. So I'm moving from the positive to the negative now is what is the exit is going to be negative. So I took off from here, that's the negative. So that negative terminal, that's the negative terminal I took off from here. Now I am now entering the resistor. According to this one is the resistor. This is a resistor. This is a 1 ohm resistor. It's written there. It's a fixed resistor. It's 1 ohm written there. So I just connect it to that resistor. Here you can so I see it there. This is a resistor. It has its terminals, but it doesn't have plus or minus. So it's just a conduit. It just allow the charges to pass through or resist them. It's a resistance. It's resisting the flow of the current by an ohm of 1. So that's why it's written here. It's fixed resistor. It's 1 ohm. So I'm using a 1 ohm resistor here. So you can see that the resistance is going to be very small. So you see that the current is going to be high because I look at a 3 volt battery. So watch this. Now this is the resistor. I have the resistor connected somewhere there. Yep. So I move from the potentiometer to the positive of the battery. From the negative of the battery, I enter the resistor. The resistor do not have plus or minus, so I just pass through. It's just a conduit. So now I pass through the resistor. This is the resistor here. So now from the resistor, I have to enter the ammeter. This is the ammeter. The ammeter measures current, so I just put this one here. Is this I'm trying to draw? This is the ammeter A. This is the scale here. So I took off here from a negative. The negative in the laboratory is black. This is black. Negative plus is red. So all terminals in the laboratory, you see plus there is red and negative is black. So I took off from a negative terminal. I passed through a conduit. This is a conduit. It doesn't have positive or negative. It just either resist the current or allow them to flow. So when I take off from a negative terminal, I entered the ammeter, which has a plus or minus. That is, it has a negative or positive terminal. So since I took off from a negative terminal, I should enter a negative terminal of this ammeter. So this is going to be negative there. So I'm entering, this is going to be a black. So I enter the black of the ammeter. So watch out, this line goes onto the black. That's what I've done so far here. So it moved from here, that's it. I enter the black of the ammeter. This is the black of the ammeter. Maybe I will remove this first, you see. Now I enter from the resistance, which is the resistor. I enter to the black components. The black is the negative. I took off from negative of the battery. Then I'm entering to the negative of the ammeter. That is the black. The black color there is the negative terminal. So I enter the black. So if I enter black, then I should take off with red. This is red. Red is positive. This is negative. So I take off with the red. So here, I'm taking off here with red. I enter here negative. So I'm entering here, I'm taking off here with the plus. So this plus goes to the key. The key do not have plus or minus, just a conduit. So now I'm taking off from the plus, then I pass through the key. Then I have the jockey. The jockey is the one that goes onto the wire and it closes the circuit there. So this is the whole circuit. So now I have moved from the key to the jockey goes onto that. So I'll just show you the stuff. So I said I move from the negative terminal, I enter the black. So if I enter the black there, I should take off from the red. So first of all, let me say something about the scale, this ammeter. This ammeter has two scales. So if I'm using, I want to read a current between 0 and 3 amps. So I'm going to read the lower scale because it is 0 to 3 amps. But if I want to read current from between 0 and 1 amps, I'm going to use the upper scale. And if I'm using this upper scales, the terminals here also changes. You see here, you see a 1 here. This is telling me if I'm reading current between 0 and 1, so I'm going to attach it here. But if I'm reading current between 0 and 3, I'm going to attach it there at this 3 amps terminal. So these two terminals will tell you which one you want to use. The black will be 1, but the positive is 2 there to tell me which one based upon my scale. I want to use this scale here. If I want to use the bottom scale, which is 0 to 3, then I'm going to make sure I connect these terminals here. But if I want to read the 0 to 1, I'll connect it here. Like that's what I want to do now. So I'm going to use 0 to 1 because I'm expecting a very small current. So let's check this out. Now I have to connect it. Now you see this is the ammeter. So I'm connecting it to the 0 to 1 scale. So I'm expecting the 0 to 1. I'm going to read the upper scale because I've connected it to the 1 amp terminal. So I'm expecting this. I'm reading the upper scale. If I wanted to read the lower scale, I connect it from here. So this is from the ammeter. So I'm taking off from the ammeter. I pass through a key. This is a key. This is a sophisticated type, but I can bring another one here. This is also a key. Watch this out. It can be. This is a key. I can also use the crocodile clip to go to this key. Somewhere here. This is. I can just connect it somewhere there. This is a key too. So it does the same work as this one. This is also a key. That's a key. This is somewhat sophisticated, but if you have local ones like this, you can try that. This is a key also, and you see this is the plug key. In that case, I'll remove the plug and close the plug. When I close here, this is terminal here. The charges will pass through there, but there's a loop here, so it could not go down. So if I have the charge, you want the charges to pass through, I have to put this conduit here. That is where the key comes in. It's called a plug key. That's a plug. I plug into the hole so the charges will pass through here. When I open it, the charges will not pass. So I've opened the key. Then I'll close the key. I open the key. I'll close the key. So when I close the key, I'm closing the circuit. So this is one of the keys that you can use. But I want to use this sophisticated type. You have some of this in your laboratory. You can use them and see you have the same outcome. So let's move this out here. So I keep this local one for now. I'm going to use this sophisticated type. So watch this. This is here. I have it somewhere there. Okay. So this is a key. I can close it. I can open it. Close. I open. So this is a key, sophisticated. But you can also use some other form of the key like this one. So from the key, I'm moving from the key. I go to the jockey. The jockey can be any lead there. I can create a jockey from here. I can just connect my constant time. I can just connect my crocodile clip here, and that jockey can move from here and goes to the wire. That's the jockey. But because I want to make it longer, I have used a black jockey here. I have adjusted it so that I can have a longer one. So this is short, but because I know that this can't get, it cannot go up to there, so I needed to make an adjustment. So I brought in this so that I can now extend this. So the jockey is now longer, so it can go up to there, it can go to whatever I want to use, I can use it here. So this is the jockey. You can use a whole straight wire, it can still give you the jockey. This crocodile clip, normally you have a jockey. I'm just using a crocodile clip in the place of the jockey. But now I can still use the jockey there. The jockey, some other day I'll show you the jockey. So let me test what is happening here. I want to test my current first. I want to test all my appliances, whether they're working properly. So I check that out before I start my reading. I want to just check the appliances. I'm just making a check so that I know that it's working. Or yeah, so now I have realized that it's working. So when I remove it, I've opened the circuit. There's nothing flowing here. But when I tap it, I'm using this constant time wire here, not these other ones. These ones are just reserved. So I put it right on it there. You don't scrape it, you tap it. So that when you scrape it, you increase the resistance of that wire. And when you increase the resistance of the wire, then you are going to affect the reading, the outcome of the experiment. So now this is just to tell me that my circuit is complete. I have connected the circuit properly and in the proper sense. That's why I'm reading it there. If I did not connect it in the proper order, the pointer here, this ammeter, will not go clockwise. It was going to go anti-clockwise, telling you that you have not connected it in the proper direction. So now this is telling me that my current is reading somehow here. That is, the circuit is now operating. So the experiment proper now starts. I can just put the key there and I'll come back to my table somewhere there. So first I have fixed everything in there. So I want to now see what will happen if I put it at 20 centimeter. Now what will happen to the current? Now this is centimeter, this is centimeter. So I'm putting this at 20 centimeter. You can do it both ways. You can first open the key and go connect it at 20 centimeter. This is 0. I'm using this scale. This is 0, 0 up to 20 centimeter. This is 17, 18, 19, 20. 20 centimeter is just there. So I can just let me see. I just use my scissors to try to locate it at 20 centimeter. This is at 20 centimeter. There, this is 20 centimeter. So now I got this. Now I connect it at 20 centimeter. If you have chalk, it's easy for you. This is at 20 centimeter there. This length is 20 centimeter. If you have chalk during the experiment, you can just mark there so that it's easy for you to attach. So the crocodile clip is now at 20 centimeter. This length is now the resistance that is offered to this circuit. So it is 20 centimeter. That's what is here. I've just measured it. So now I want to record the time, the current that is going to flow in there. And what I did was to open the key first whilst I connect it there. You can do both ways, the reverse. You can as well close the key, then you try to connect it there directly. Or you connect directly there, then I come and close the key. I'm trying to close the key now. When I close the key, now after connecting it there, this is it. So I close the key. So when I close the key, yes, I have it on this. I just tap it there. Now it was at 20 centimeter. I just fix it there at 20 centimeter. So you can do either ways. I place it on the 20 centimeter. So at the 20 centimeter mark, this is the current that is flowing. So I use the 1 amp scale. So the 1 amp scale is right off there. That is 0.2. So it's on 0.4. 0.4 is stable on 0.4. So what that? So I can just say it's 0.4 there. So now I remove it from there. So I'll record it as 0.4. This is 0.40. So I am going to fix it at. So I close the key. I want to now fix it. I measured it first at 20 centimeter. That was somewhere around here. Now I'm going to put it at 40 centimeter from my scale over there. It's 40 centimeter. This is 41. It's 40. So 40 is somewhere here. So So I tap it at 40 centimeter here. So if I put it on 40 centimeter, you see the current is dropping. So this one is 0.3, it's just 0.3, stable at 0.3, 0.3. So let's say 0.3, it's around 0.3, stable there. So let's say 0.3, I have it at 0.30. So I'm moving to the next one is 60 centimeter. I have this is I'm still moving. This is 10, 20. This is 40, 40. This is 50. No, 59. This is 60. So I put it at 60. This is 60. I tap it at 60. That is 60. So I just tap it there. So see what is happening. Now it is somewhere around 0. Then allow it to be stable somehow. Yes, it's somewhere around 0. So I put it right here. So it's somewhere around 0.2. It's not stable, but let's see what will happen there. So I do it again. This is 60 centimeter. I just put it somewhere there. So now it is a little above 0.2. It's just around 0.2 there. So it is stable at 0.2. You know, it's the current is not too stable, but it's around 0.2. And you can see it from there. It's around 0.2. So now this is 0.2 as it is stable there. Now, so I have it at 0.20. Now, all right. So we've been able to look at the 20 centimeter. I place it somewhere there and got that figure, and 40 centimeter I place it there. I got 0.3, and 60 centimeter 0.2. So we want to use these three values and try to see a relationship between them. So let's look at what is established here. Remember, I said that the length is inversely proportional to the current. So as the length is increasing, what will happen to the current? The current must be dropping. So let's see whether that relationship holds in this experiment, what we did just now. So when I place it on the 20 centimeter mark, this was the current. You know, my battery is not new, so I expect some of these figures. But when you do it in the laboratory, with a very sophisticated material or battery, you could be able to see the variations there. But it's going to give you the relationship. It means that when the resistance is increasing, the current must be falling, and that's what we have seen here. As I increase the length from 20 to 40, it reduced from 0.4 to 0.3. So it was dropping by 0.1. Since I'm increasing the resistance, if I increase the length, the resistance also going to increase, because the resistance is directly proportional to that length. So the length of the constant time wire here, this air here, as it is increasing, that's how the current is dropping there. So if you now look at the relationship, you can now say, okay, let me plot this on the, I put I on the x-axis, I put that I on the y-axis, I put the x on the horizontal axis. So I have, let's say 20, then I have 40, then I have 60, then I'll have 0.2, 0.2, 0.4, 0.6, the current there. So now, if we plot this graph, we want to see the relationship of that sketch. The amperes is measured, the current is measured in amperes, and this one is measured in centimeter from our rule. You can also measure it in meters if you like. This is 0.4. 0.4 corresponds to 20, so 0.4 to 20, that is here. Yeah, so now we have 40 centimeter is corresponding to 0.3, so 0.3 is somewhere here, so we have 40 centimeter. So I have 40 centimeter there. This is, and look at 0.2 correspond to 60. 60 is 0.2. 0.2 is somewhere there. So now if you draw the line, you will see that it's a straight line through those points. Somewhere here. So it's telling you that there is an inverse proportionality. I is inversely proportional to L. That is, I is inversely proportional to R, since R is directly proportional to L. So you have seen the relationship. As the length was increasing, the current was dropping, and vice versa. Now you'll be asked to, maybe you want to transform this graph into a direct graph. You can now have I inverse or L inverse. If you do the two there, the one is going to change upside down, so you have a direct graph. If you do that now, you now have a direct graph going that way. So it's one way we can establish this. So watch out again for the summary. I said that the potentiometer wire, it contains the constant time wire. That's just what we saw over there. And we have the leads here. The leads are connecting wires. So in this experiment, you have like 6 connecting or 5 connecting wires, excluding the jockey. So if you include the jockey, you have 6 there. So you have 1, 2, 3, 4, 5. Let's say 5. Okay, 5 connecting wires, that's what we have here. So if we have a cell, the cell is there. Remember this symbol here, this long line here is positive terminal, this negative terminal, and we have the resistor, that's what was here, and we have the resistor that way. So I can go back there. This is the line going to the, now the positive terminal, the long guy is the positive terminal, and this short line is the negative terminal. Negative terminal to the resistor, that's the resistor. From the resistor, we enter the ammeter, that's the ammeter. From the ammeter, we enter the key then to the jockey onto the, that's how the circuit is completed. This jockey goes onto the wire, so we have the complete circuit there. And that's how we were able to check the current flowing through. If you can see that if you put you reduce the length very well there, you see the current is higher. Because I have reduced the length, the current is very high over there. Because the current, the length is now smaller, so the current goes there. So if you remove it from here, maybe we want to put it at the extreme here also, you will see that the current has fallen. It was somewhere around 0.4. But when I reduce the length, it went down. It's telling you that the moment you increase the length, it's going to be an increase in the resistance. And the increase in the resistance will give you will drop the current for you. That's what happened over there, as you see from the experiment. So let's look at the relationship between them. Like I said, we wanted to establish the relationship between the current and the resistance. We were able to look at the relationship between the resistance and the length. We know that the length of the constant time wire is directly proportional to its resistance. So if I increase the length, by extension I'm increasing the resistance, and vice versa. So now if you increase the resistance, then according to Ohm's law, you are expecting the current to come down. So because their opposition to the flow of current is increased. When you oppose the current much more, the current will flow less. And when you do not oppose the current will flow high. That's the relationship we wanted to establish. And we came to this, we saw from our values that there is a link between the length and the current. When the current is increasing, when the length is increasing, from 20 to 40 centimeters, 60 centimeters, the resistance was increasing as well. And when the resistance increases, then the opposition to the flow of current also increases. And as the opposition increases, then you don't expect current to flow much. The currents keep dropping because I'm increasing the resistance. So that's the relationship we are able to establish. So you now look at this experiment, find your own laboratory materials, and you try to fix it up. But watch out for the scale. When you start here, it is the 0 end. That's why we are measuring the 0 to the 100 centimeter. So watch out the scaling so that you don't start with 100. You know, so now you starting on 0 here so that you get a count here. This is, and you don't tap, you don't scrape the wire. You don't scrape the constant time wire, that is the crocodile clip or the jockey. You cannot scrape it on it. You just tap. You are tapping it, because if you scrape, you are going to increase the resistance of the wire and the experiment will have fault. So that is why you ensure that this. So watch out for the basic connections. Ammeters are always connected in series with the circuit. It should be in series with the battery. And voltmeters are the ones that are connected in parallel. So note that the next circuit we are going to talk about later on is going to be a voltmeter. So watch out and keep subscribing. And make sure you follow me up as I give you more lessons there. So we're going to stop here for today, and you keep following as I'm bringing more videos. Don't forget to subscribe. My name is Mr. Samuel G. Koidia, and I wish to see you in the next lesson needs to continue again. So thank you for your audience, and let's keep watching and expecting more to come from me. Thank you.